Um, hey SM3, so this is 4.2, and we're learning a little bit more about rational exponents and radicals. So, um, we learned a little bit about it last time, so we're just continuing on with that theme. So, we're going to be using properties of exponents here. So, this first page should just be a reference page for all of you. So, it just has a bunch of formulas that are useful to know. All of these right here, the property names as well. I'm not really expecting anyone to memorize these, although that being said, it's something that you guys should be able to be familiar with. So these properties shouldn't be something that you have to memorize really. Instead, it's something that you use a lot, you practice a lot with, and therefore you get familiar with the property themselves, and so it just becomes natural to use the properties. So all I would say is that practice them a lot instead of memorizing, because the more you practice, the more they'll be embedded into your memory. It'll just come to you naturally, the properties of exponents and radicals. So we'll refer back to these a lot whenever we're going through these examples. So for the first one, example A number 1, again we're using properties of rational exponents to simplify. So if I were to give you x squared times x to the 6, I think most of you would answer that this would be equal to x to the 8th power. And you know that because this is x times x, and then this is x times x times x 6 times. So total you would have 8 x's being multiplied by one another. So a shortcut would just be to add the exponents, and the only reason you can add the exponents is because the base is the same. So that is what we call the product of powers, is that whenever you have the same base and if you're multiplying, you can add the exponents here. So the a to the power of m times a to the power of n is the same thing as a to the power of m plus n. So here we have a similar base of 7, and so all I have to do, and you see that they're being multiplied, that's also a key here, is that now I can just add the exponents. So 1/4 times 1/2, well, I need to add these, so I have to make sure that the bases are the same. So I'm going to rewrite 1/2 so that it has a base of 4. So 1/2 is the same thing as 2/4. So now that they have a similar base, I can add the numerators. So 2 plus 1. So that's equal to 3 divided by 4. So this is equal to 7 to the 3 over 4. Now if we go to B, you see that we're multiplying here, but the bases are not the same. So that means we can't add the exponents. So let's see what property we can use up here. So we see that we can't do anything here, but we also have this whole thing being raised to the power of 2. So let's look at our properties, and if we see here, we have a power of a power. So anytime we have something, or sorry, not the right one, the power of a product, you see that we have two different items being multiplied inside, and they're both being raised to a power. And so this is the same thing as a to the m times b to the m, so you see that this m is somewhat distributing to both the a and the b, only because the a and the b are being multiplied by each other. So what I could do is I can distribute this to both terms, so that this is now going to be 6 to the 1/2 squared times 4 to the 1/3 squared. Now what I can do is I see that I have a power to a power, that I have a to the m to the n. And whenever you have a power to a power, you can multiply the exponents together. So you see I have 6 that's raised to the 1/2 power, that's raised to the 2nd power, so I can multiply the exponents. So I have 6 to the 1/2 times by 2 times by 4 to the 1/3 times by 2. Well, 6 1/2 times by 2 is just 1, so that's just going to be 6. Times by 4 and 1/3 times by 2 is 2/3. So that's simplified as much as we can get it. And that's that right there. Okay, so let's go to C. And I'm going to use the same power. So I have -1 to the 5th out here, so I'm going to distribute that across both of those. So I have 4 to the 5th power to the -1/5 power times by 3 to the 5th power to the -1/5 power. So that's equal to 4 to the 5th times by -1/5 times by 3 to the 5th times -1/5. Well, 4 to the 5 times by -1/5 that's -1, and that's going to be the same here. So 4 to the -1, 3 to the -1. Now we have a new rule. So what can we do with negative exponents? So we have that one right here. So with negative exponents is the same thing as the reciprocal of it, but with positive. So you see here that a to the -m is the same thing as 1 divided by a to the m, positive m. So that's what we can do with negative exponents. So this would be equivalent to 1/4 to the 1st power times by 1/3 to the 1st power. And anything to the 1st power is just itself. So this is equivalent to 1/12 because we can multiply across. Something that I want everyone to remember here is that never distribute exponents across anything but multiplication and division. So for instance, if you ever see a plus or minus b squared, this does not equal a squared plus or minus b squared. I can't distribute the exponent across to the a and the b because we're multiplying or we're adding or subtracting here. Notice that we can in this case because the operation is multiplication. So never forget that. Don't distribute across addition or subtraction. It won't work. Alright, so I have, for D, I have 5. We can basically call this 5 to the 1 divided by 5 to the 1/3. So this is what we call the quotient of powers. So you notice here that we have the same base, just different exponents. So if you have a to the m divided by a to the n, this is the same thing as a to the m minus n. So this is like the opposite of the product of powers, where instead of multiplication, we now have division. So here, this could be equal to 5 to the 1 minus 1/3. So now I have to take 1 and minus 1/3. So let's rewrite 1 so that it has a denominator of 3. So I can rewrite that as 3/3 minus 1/3. So that's equal to 2/3. So I have 5 raised to the 2/3 power. Alright, now for E, this one looks pretty complicated. The good thing is about properties of exponents is that you can go about it in multiple ways. So one thing I could do is I could distribute that 2 to both of them. But there's also another thing I can do. So you see here that the power of a quotient says that if a divided by m, if both of these are being raised to the m power, then this is equivalent to a to the m, b to the m. So if I do this in reverse, a to the m power times b to the m power, notice that they have a different base, but they have the same exponent, then I can rewrite that to be a divided by b to the m power. So I can rewrite this to be 42 divided by 6 to the 1/3 power, and that's being squared. So now there's two things I can do. First, I can perform 42 divided by 6, which would be 7. And then I can multiply this 2 and this 1/3, because that's a power to a power. So then this now becomes 7 to the 2/3. So first thing, I could have done this in reverse. I could have done 2 multiplied, distribute it to the 1/3. And then what I could have done is done the same thing. So either way, I'm making the same steps, but I'm doing it in a different order. Alright, now this is going to be using properties of radicals, and that's what this is right here. So the properties of radicals are pretty easy. There's two properties. There's the product and the quotient. And this is their definition. So if you have a radical of a times by b, this is the same thing as the radical as the nth root of a times the nth root of b. So basically you can split this up to be under the same radical. Now the definitions also apply the other way around. And the quotient property is the same thing except with division. So here you see that we have the 3rd root of 12 times the 3rd root of 18. So this is equivalent to the 3rd root of 12 times by 18. So what we did here was the opposite. So we had the 3rd root of 12 times the 3rd root of 18. So this is equivalent to 12 times 18 all under the 3rd root. So that's the property that we used. Now I can do 12 times 18. And that's equal to 216. So this is the 3rd root of 216. Now, what multiplied by itself 3 times is 216, and that's going to be 6. Alright, so now I have, for b, the 4th root of 80 divided by the 4th root of 5. So since it's division, I know I'm going to use a quotient property. So I'm going to be using this in reverse, where I can take the 4th root of 80 divided by 5. So let's do 80 divided by 5, and that's equal to 16. So I have the 4th root of 16. So what multiplied by itself 4 times is 16, and that's going to be 2, plus or minus 2. Okay. Now let's go to 3. So we're using radicals again. So I have for a the 3rd root of 135. Now the 3rd root of 135, I don't think I can take that. I'll probably get a decimal number. So what I have to do is I have to reduce 135. So I have to think of factors of 135. But I need to think of a factor that I can take the 3rd root of. Okay? So let's think of 135. Let's try and divide this. So I know that that's divisible by 5. So 5 and 27. So that's actually really helpful. So I know that this is the same thing as 5 times 27. So this is equivalent to the 3rd root of 5 times 27. Now, this is good because I can break it up to be the 3rd root of 5 times the 3rd root of 27. So now I have the 3rd root of 5 times the 3rd root of 27. which is good because the third root of 27 is easy to find. It's a number multiplied by itself 3 times, that equals 27, and that is equal to 3. So I have the third root of 5 times by 3. I'm going to write that as 3 times the third root of 5. Alright, so for this one, it was just, I noticed that I can't take the third root of 135. So can I break it up into factors, and are there any factors of 135 that I can take the third root of? And therefore I can simplify using the product property of radicals. Alright, let's jump to b. So for b, I have the fifth root of 7, which I don't think I could find, and the fifth root of 8, which again, I don't think I can find. So the problem here is that I have a radical in my denominator, and we often don't like to have radicals in denominators. So let's think of a way that we can get rid of this radical in the denominator. So I have the fifth root of 8, which I know I can't take. But is there something I can take the fifth root of? So I know if I take 2 and if I multiply that 5 times, I'm going to get, that's going to be 4, that's going to be 4, this is going to be 16, and this is going to be 32. This is good information because I know I can take the fifth root of 32 and get 2. So is there any way I can change the denominator to be the fifth root of 32? So to do that, I would have to multiply this to be, multiply that by the fifth root of, well, what is 8 times, what do I need to multiply 8 by to get 32? And I believe that should be 4. So if I multiply this by the fifth root of 4, then I will get, in the denominator, the fifth root of 8 times by 4, which would be equal to the fifth root of 32, which I know is equal to 2. Now the problem here is that if I multiply the denominator, I also have to multiply the numerator. So I have to multiply this by the fifth root of 4 as well. So now I have the fifth root of 7 times by 4, which is equivalent to the fifth root of 28. So at the end I will have the fifth root of 28 divided by 2. And I can't take the fifth root of 28, and that's as simplified as it can go. So that would be my answer. So you see here, I saw that I had a radical in my denominator, and I don't want that. So I just had to think of a way to get rid of the radical. Okay. Now let's jump to example 4. So writing a radical expression in simplest form again. So again, I have a radical in my denominator, which is something I don't want. So, but the thing is, I can't multiply this by the square root of 3 because that won't eliminate my radical. So, I can't eliminate it because I have this 5 plus the square root of 3. So hopefully you guys remember from the last unit what conjugates are. So conjugates are helpful because it helps us get rid of these terms right here. So the conjugates are, for example, a plus the square root of b. Then its conjugate would be a minus the square root of b. Now what's great about conjugates is that if you multiply them together, it eliminates the square root. So the conjugate, so if I have 5 plus the square root of 3, its conjugate is 5 minus the square root of 3. So let's take 1 over 5 plus the square root of 3 and multiply the denominator by the conjugate, 5 minus the square root of 3. But if I multiply the denominator by something, I also have to multiply the numerator by the same thing. Now, with multiplication of fractions, you can just multiply across. So 1 times by 5 minus the square root of 3 is just 5 minus the square root of 3. Now, when I multiply this together, so 5 plus the square root of 3 times by 5 minus the square root of 3, I'm going to have to FOIL or use distribution for this. So I'm going to multiply the 5 and that together. So I have 5 minus the square root of 3. So 5 times by 5 is 25. And 5 times the square root, a negative square root of 3 is negative 5 square root of 3. And then I have to multiply these together. So positive square root of 3 times by 5 is just positive 5 square root of 3. And then I have, then I have square root of 3 times negative square root of 3. So that's going to be minus the square root of 9, because this is equal to the square root, negative square root of 3 times by 3, which is equal to negative square root of 9. Now I can simplify this even further. So notice here that these cancel. Also, I lied to you guys. That's not right. Oh wait, I think it is right. I'm just thinking different. I'll explain in just a second. But in any case, so you see that this, I have a positive 5 square root of 3, and I have so I have both a positive and a negative 5 square root of 3. So those will cancel, which is why we want to use conjugates, because those will cancel out really easily. So I'm left with 25 minus, and I know that the square root of 9 is 3. So I have 5 minus the square root of 3 over 25 minus 3, and that's just going to be 22. So this is in its simplified form. So we call this rationalizing the denominator, which means we're getting rid of conjugates. So notice here that our denominator doesn't have any conjugates. And that's it for that. Alright, let's jump to 5. So adding and subtracting light radical roots. So here we have the the fourth root of 10 plus 7 times the fourth root of 10. So imagine that the fourth root of 10 is just x, right? So we have x plus 7x. So you see that we can treat the fourth root of 10 as if it were a variable. So in this case, if we had 1 fourth root of 10 right here, so this is 1 fourth root of 10, and here are 7 fourth root of 10s, so we can combine them to just be 8 fourth root of 10s. And that's really as easy as it is. So for b, you see that this is 2 times 8 to the 1/5 power, or we could say that this is 2 times the 5th root of 8. So then plus 10 times the 5th root of 8. So this is equal to 12 times the 5th root of 8. So here I have 2 5th root of 8s, and here I have 10 5th root of 8s. So that's equal to 12 5th root of 8s. I'm just treating these as variables. Okay, now for c, I have the cubed root of 54 minus the cubed root of 2. So you notice that these are not the same. It was good here because the variables we were able to treat as the same. So is there any way we can simplify this term right here to be the third root of 2? So let's take 54. Now, the thing is, I know that it's 54 divisible by 8. So it's not divisible by 8. So what I'm trying to do is I'm trying to reduce this by finding factors of 54 that I can take the third root of. So what about 54 divided by, I think it's divisible by 2, and so 27, which is good. So this is the same thing as the third root of 27 times by 2. This is good, because then I could split this up to be the third root of 27 times the third root of 2. And I know the third root of 27 is 3, so I have 3 third root of 2 minus the third root of 2. So you see now I have, I guess you could say, like terms. So I have 3 root of 2 minus 1 third root of 2, which would be equal to 2 third root of 2. So the trick here was just to change it so that it was something that had the third root of 2. Now let's jump to 8. So it's kind of we're doing the same thing. Okay, perform each indicated operation. So for a, it's 5 times the square root of y plus 6 times the square root of y. So again, I'm going to treat this square root of y as if it were something like x. So you see I have 5 square root of y and 6 square root of y, and if I add them together, I'll get 11 square root of y. And then for b, so again, I can't add these quite yet because 1 is the third root of 54 z squared and 1 is the third root of 2 z squared. Now this is almost pretty much identical to this answer right here. Right? I'm taking the third root of these, so I want to simplify this right here. So this is going to be 12 third root of 2z to the 5th power. Okay. Now what I want to do here, so I have z times the third root of 27 times by 2 z squared. So basically I'm just splitting up this 54. So then this now becomes z third root of 27 times 2 third root of 2 z squared. And the third root of 27, like we discussed, was 2. So I have 12 third root of 2z to the 5th minus z times by 3 times by the third root of 2z squared. So if it helps you, it does to me sometimes, but basically what I'm trying to do here is to envision the third root of 2 z squared as if it were equal to x. So I'm not quite there yet because, as you can see here, I have z to the 5th power right there. So this needs to be simplified just a little bit more. So I'm just going to take the third root of 2z to the 5th. Now I'm going to change this. I want to make sure that this is the square root like it is over here. So I know that this is equivalent to the third root of 2 times by z to the third times by z squared. Now the thing about this is that this is z cubed. I could rewrite this to be the third root of 2 times the third root of z cubed times the third root of z squared. So here I have the third root of z cubed, which is just equal to z. So if I put that out here, that goes away, right? So that's just equal to z. So then I'm left with the third root of 2z squared, which is perfect because that's what I wanted. I want to represent the third root of 2z squared as x. So now I just reduced this to be 12z, because we were able to bring a z out, times the third root of 2z squared minus z. I guess I could write 3z, third root of 2z squared. So you see here that I now have like terms, where I could basically say that this is, I guess, 12zx, because I can make a little substitution if it makes sense to you guys, minus 3zx. So in short, this would be equal to 9zx, or I can write that as 9z times the third root of 2z squared. So that one was a bit complicated, but I'm just using the properties that I'm familiar with, right? I'm using I'm using the product property, and then I'm using like terms to add and subtract these expressions. Okay, so that should be everything that you should need for the homework. It should get you everything that where you need to be. So if you have any questions, just email me. If not, I'll see you guys in class.